Hello, today we continue in our A-level physics revision series looking at waves. Waves carry energy, X-rays penetrate your body, sound waves can make things vibrate, water waves can knock you over in the sea, and infrared waves can warm you up. A wave looks like this. And we say that the distance between two crests is the wavelength, lambda. And the maximum displacement is called the amplitude, A. We say that the number of waves, or the number of peak, the crest of the wave, the number of crests that pass a point in 1 second is called the frequency. And we say that the time it takes for one wave to travel, for one crest to travel to the point of the next crest, is called the period of the wave, which is t. And t is 1 over f. Because if f is the number of waves which pass a fixed point per second, then the time it takes for each succeeding crest to reach this point is 1 over f. This axis here, of course, is simply the distance travelled by the wave. And waves have particular characteristics. They can be reflected, they can be refracted, they can be diffracted, and they can show interference patterns. The speed of a wave is the speed, like the speed of anything else. It's the distance divided by the time taken to travel that distance. And if we think that the distance is the wavelength, what is the time taken to travel that wavelength? Well, the answer is, of course, t. So the speed of a wave is lambda divided by t. But t is 1 over f. And so that is one and the same thing as lambda f. So the speed of a wave is its wavelength times its frequency. And that's its speed. These waves are called transverse waves. But you can also have what are called longitudinal waves. And sound waves are longitudinal waves. Basically, if you have columns like this, then a longitudinal wave will bunch some of these up and stretch some out. So at one moment you might have that kind of arrangement, and then the next moment you might have that kind of arrangement. There's, instead of it being transverse, going up and down, it actually goes in and out, rather like a concertina. Transverse waves can be polarised, because although I have depicted a transverse wave like this, in truth it can of course oscillate in any direction. If you were to look at that wave as it were head on, then you would see it oscillating up and down. But there's no reason why it shouldn't oscillate that way, or that way, or that way, or indeed in any way. And that's an unpolarised wave. But you can force it to travel only in the up and down direction. And that would then become a polarised wave. And waves can be polarised by passing them through a polarizer. And the polarizer will take unpolarised light and polarise it in its direction, so it will go up and down. But of course you could twist this polarizer round so that it would only polarise light in that direction. You just have to twist it through 90 degrees, and then the light will be polarised in this direction. What that means is that if we take a polarizer which will polarise light in that direction, then unpolarised light going through it will come out polarised. So here it's unpolarised, here it's polarised. If we then put it through another polarizer that polarises light in that direction, the light that goes through it is only polarised in that direction, and that won't get through. So you won't get any light going through polarizers where one of them is vertical and the other is horizontal. Now, light is an electromagnetic wave, and electromagnetic waves are transverse waves. Electromagnetic waves do what they say on the tin. They are made up of electric and magnetic waves. The electric wave looks like this. The magnetic wave is at right angles to it, 90 degrees, so it looks something like this. So here's the electric field going up and down, and here's the magnetic field going, as it were, back and forth. This is the electric field, this is the magnetic field, and you'll notice that they are what's called in phase with one another. This has a crest when this has a crest. They both reach a minimum at the same point. They are in phase. And all electromagnetic waves travel at the same speed. It's the speed of light, and it's 2.998 times 10 to the 8th meters per second. And we sometimes round that to 3 times 10 to the 8th meters per second for ease of calculation. It was James Clerk Maxwell who showed that the speed of light is equal to 1 divided by the square root of mu0 epsilon 0, where mu0 is the permeability of free space and epsilon 0 is the permittivity of free space, and we've met both those terms before. The equation which shows you what the force is between two charges says that the force is equal to the value of one charge times the value of another charge, those are electric charges, divided by 4 pi epsilon 0 r, where r is the distance between the charges, and that epsilon 0 is that one. Similarly, we also found that when you pass a current through a wire, there is a magnetic field generated around the wire, and the value of that field, B, is equal to mu0 I, where I is the current, divided by 2 pi r, where r is the distance from the wire. And that mu0 is that mu0 there. So those two terms that we're already familiar with, if you put them into this equation, that derives the speed of light. We're now going to look at the electromagnetic spectrum. We've said that the speed of a wave is equal to its wavelength times its frequency. And for electromagnetic radiation, all waves travel at the speed of light, c. What the electromagnetic spectrum recognises is that you can have different wavelengths and different frequencies, but the wavelength multiplied by the frequency must always equal the constant c. And that means that if the frequency goes up, the wavelength must go down, and vice versa. So here we're going to draw the electromagnetic spectrum. This end will be high frequency, but therefore low wavelength, and this end will be low frequency and therefore high wavelength. And what we find is that at the low frequency, high wavelength end, we have the radio waves that are used to transmit radio signals. At a slightly higher frequency, slightly lower wavelength, we have microwaves. And it's in this region that the television signals are transmitted. Then we have infrared radiation, that's basically heat. And then there's a very small section of the electromagnetic spectrum which is visible light, which goes from red right the way up to violet through the colours of the rainbow. And then we have ultraviolet, which is what can do damage to your skin. And then we have X-rays. And finally we have gamma rays and cosmic rays, which come from the sun. And you'll see that as we go in this direction, the waves get more dangerous. That's because they carry more energy. The further you go along in this direction, the more energetic the wave. And it was Einstein who showed that the energy of a photon which is the particle of light or the particle of electromagnetic radiation, is equal to Planck's constant h times the frequency of the radiation. So as we go in this direction, frequency is increasing. And so if frequency is increasing, so the energy of the wave is also increasing. Intensity is a measure of the energy in a wave. It's the brightness of light. It's the loudness of sound. It's the rate of flow of energy. And it's proportional to the amplitude of the wave. You remember that we described the wave like this, and we said that the maximum displacement was called the amplitude. And the bigger the amplitude, the greater the energy. In fact, the intensity is proportional to the amplitude squared. Let's now think of a point source of light which has a power P. That light will spread out in all directions. I can only show it in 2 dimensions, but it will of course spread out in all directions towards me and away from me. But we'll represent that this is a sphere, not just a circle. That's a sphere of radius r. And I'm going to observe the light at a radius r from the point that has a power P. What intensity will I observe? Well, I'll observe the power, but the power has now been spread out across the whole of the surface area of the sphere, which is 4 pi r squared. So the intensity that I see is simply the power as it is distributed across the surface area of that sphere. And that tells me that the intensity is proportional to 1 over r squared. It's what's called an inverse square law. If you go double the distance, the intensity will fall off fourfold. One feature of waves is that they are capable of what's called superposition. That means that if you take a wave like this travelling in this direction, and that meets a wave like this travelling in this direction, when they meet, they will actually pass through one another, but when they actually meet, they will provide or produce a double crest. Similarly, 2 troughs meeting will produce a double trough. But if you have a crest travelling in that direction, meeting a trough travelling in that direction, then at the point they meet, they simply cancel each other out. And that's the principle of superposition. And we call these two constructive interference. And this one we call destructive interference. You can see examples of this if you throw 2 stones into a pond. This is the position where the 2 stones go in. Each stone will produce ripples on the pond, and it's where they overlap that you see the interference patterns. You will see both crests, where 2 waves come and reinforce one another, and you will see positions where the 2 waves cancel each other out. I now want to look at standing waves. Standing waves carry no energy because they don't actually go anywhere. You can create a standing wave by taking a piece of string and fixing it at one end and then giving it a slight flip at the other end, and that will generate a wave that will flow along the string until it gets to the fixed point. And when it gets there, it will be reflected back but upside down. Now you can of course wiggle the string several times to send several of these pulses going down, and they will be reflected back. And as they are reflected, as this wave meets this wave, then there will be some form of interference, either constructive or destructive. And for most of the time, you just get a mess. But you can get to a situation which is called resonance, which is where the advancing wave and the reflected wave form what's called a standing wave. And typically what happens is that the first such wave that you derive is this kind of wave, where the wave is simply oscillating up and down. It's going like up, down, like this. That's a standing wave, and that's called the first harmonic, or the fundamental frequency. And you can do that with a rope or a piece of string. And you'll see that the distance here is half a wavelength, because a full wavelength would be this distance, but we've only got that bit of it. So that's half a wavelength. Let's push it up so you can see it. That would be a full wave. That, which is what we've got here, is half a wavelength. But that isn't the only harmonic that we can achieve with that string. We could also achieve something that looks like that, where the wave will now go up and down in this kind of way, oscillating alternately. And now we've got a wave that is indeed one wavelength long. And that is called the second harmonic. We could indeed go further. And now we can have this shape. These 2 points here, and indeed this point here, are called nodes. They never move. They are always zero. And here, these 2 points are moving up and down, and this point is going down and up in opposition to these oscillations here. And that would be called the second harmonic. And the wavelength, or the total length of that wave, is 1.5 times lambda, because this is a full wavelength and this is another half wavelength. This is exactly what happens with a guitar string. A guitar string will oscillate in all these modes and many more besides: the fundamental, the first harmonic, the second harmonic. And that's the reason why different instruments produce different sounds. They might all play the same note, which means that they are all playing the same fundamental, but they will all have slightly different harmonics, and it's those harmonics that give the instrument their distinctive sound or tone. Now, the frequency of a string is determined by its length, and as the length goes up, the frequency goes down. Its weight, and as the weight goes up, the frequency goes down. And its tension T, and as the tension goes up, the frequency goes up. And you'll see this if you look at a piano. You'll find that for low frequency, that's the low notes, the length of the string is longer. You'll also find that for low notes, they use a thicker and therefore heavier, more weighty string. And the tension generally on pianos and guitars determines the frequency. The more you tighten the string, the greater the frequency, the higher the note. We now turn to diffraction. Diffraction happens when you pass waves through a narrow slit. And if here are the waves coming in this direction, if you pass waves that have a wavelength lambda through a gap which is broadly the same size as the wavelength, then the wave spreads out as it goes through. By contrast, if the gap is very large, then the waves simply go through it unchanged. And if the gap is extremely small and very much smaller than the wavelength, then the waves come along and are simply rebounded or reflected. They don't go through at all. This is the reason, for example, why you can hear someone talking in another room, but you can't see them. The sound waves are broadly of the same wavelength as the door opening, so the sound waves will diffract through the door. But the light waves have a very much smaller wavelength than the door opening, and so consequently they go through it, but they don't bend round it. We can use this example here for what's called the single slit experiment. We take a slit which is of width d, and we send light waves towards the slit. And we know that the light waves will spread out. What we will actually find is that they fan out like this onto a screen. and you will find that that area of the screen will be light, and beyond it, it will be dark. There will, for various reasons, be a little bit of light beyond it, but not very much. The bulk of the light is here, and the intensity, if I can draw it this way, looks like this. In other words, in the centre, there will be the highest intensity, and then it falls off to a point where it's 0 at these points here. And that angle there is theta. And that is a measure of the spread of the light. And what we shall show in a moment is that the sine of theta is equal to the wavelength of the light divided by the slit width, d. How can we show that? Well, let's magnify the slit. This is now the slit, and it's a width, d. That gap is d. And here are light coming from the bottom of the slit and the top of the slit, and it's travelling at angle theta, which means that this is the point at which there will be no light on the screen at all. That's the point where it gets dark. What I'm going to do is to drop a perpendicular down here, that is at right angles, and this distance here we know is d, the width of the slit. What happens if this distance here, that's from this point to this point, is lambda, that is the wavelength of the light that's coming through the slit? Well, then I think you can say that if we go halfway up, by symmetry, that is going to be lambda over 2. That angle, by the way, is the same as that angle there. That angle will be theta. Now what this means is, let's draw that. That's light that is coming from right in the middle of the slit. That the light that comes from the top of the slit and the light that comes from the middle of the slit will be a half a wavelength out of phase. In other words, this light looks like this. This light looks like this. And by superposition, the two will cancel each other out. So that light beam cancels that light beam. Similarly, this light beam and this light beam are also lambda out of 2, or out of phase by half a wavelength, because this is lambda over 2 and this is lambda. So the same principle will happen here. So that light beam and that light beam will cancel each other out. And the point is that every point in that half of the slit will cancel every point in that half of the slit. That point there will have a corresponding point there, and those two waves will be exactly out of phase by half a wavelength, and they'll cancel out. So every light beam in this half cancels every light beam in that half, and that's what produces the darkness. And what we can see in those circumstances is that lambda divided by d is sine theta. That's simple trigonometry. Lambda divided by d is sine theta. That distance is lambda, that distance is d, that angle is theta. And what you can also see from this is that as d decreases, then theta will increase. So if you make the gap smaller, curiously, the light spreads out more. We can now move to the so-called double slit experiment. This is pretty much similar to the one we've already looked at, except there are now 2 slits instead of 1. And it is the distance between the slits that is now d. Beforehand, the actual slit had a width of d. Now we're going to imagine that the slits are pretty much infinitesimally small, but the distance between them is d. And as we've already shown, that light going through will spread out, and since there are now 2 effective sources for the light, we will get interference as the 2 light beams spread out. And that will produce on a screen what are called interference fringes. The screen will be over here, and that will be a distance, capital D, away from the slits. Why do you get fringes? Well, let's magnify it again. Here are the 2 slits. Here is the light beam coming from one slit, and here is the light beam coming from another slit, and we'll call that angle theta. We'll drop a perpendicular down here. This distance, which is the distance between the slits, is d, and that angle is the same as this angle. It is theta. Now suppose this distance here is lambda. That is the distance from here to here. What do we know? We know that this light beam and this light beam are exactly one wavelength apart. So we will have a wave like this, and then we will have another wave like this. In other words, they will be in phase, but simply one whole wavelength apart. And that means that they will reinforce. You will get constructive interference. So if you are looking at the combined effect of these two beams, what you will see is a constructive interference, a bright light, and that is one of the bright fringes that you will see. And the maths is quite simple now. Lambda divided by d is equal to sine theta. But that now is the condition for a bright light, because the waves are in phase. Every wave is exactly one wavelength behind the other, so they're always going to be in phase, and that gives you a bright light. But that doesn't only happen if this distance is lambda. That will happen if this distance is any multiple, as long as it's an integral multiple of lambda. As long as it's a whole number of wavelengths different, it will still constructively interfere and produce a fringe. And so you can have not lambda, but n lambda, where n is any whole number integral. And that means, of course, that if you look at the experiment, here's the double slit, here's the screen, you will certainly get a fringe. Let me draw it. You will certainly get a fringe here. You will also get a fringe at this point, which is theta when there is one wavelength between the two beams. You'll also get a fringe when you get theta 2, where there are two wavelengths. And you'll also get a fringe when you've got theta 3, that is, the difference is 3 wavelengths. And there can be as many as you can fit in. Of course, you can never get a spread that goes more than 90 degrees. The spread can't go backwards. So once you've got to 90 degrees, you can't have any more spread. But every one of these will represent a fringe on the screen. So let's look again. Here's the slit, the double slit, we'll just mark like that. Here's the screen. The screen is a distance d away from the double slit. Here's the first fringe spacing, and that is going to be a distance x. And this angle is theta. And we know, because we've just shown it, that n lambda over d equals sine theta. So n lambda over d equals sine theta, but sine theta is simply x over capital D. M lambda over d is sine theta, but sine theta is x over capital D. And so we now can, if we know the wavelength, we know the gap between the slits, we know the distance from the slit to the screen, we can calculate how far up the screen the first fringe will be if n is 1. We can also work out what x will be if n is 2, and so on. A diffraction grating works in exactly the same way as a double slit, except instead of having 2 slits, it has maybe thousands of slits per inch. And what happens is you get exactly the same thing, you get exactly the same diffraction, but the fringes, instead of being, I'm now drawing fringes, that's the double slit fringes. If you were to look at a diffraction fringe, it would be much, much sharper. So the benefit of diffraction gratings is that you get much sharper fringes, but the mathematics is still the same. Now, everything we have done so far is for monochromatic light, that is for light of one particular wavelength. If you put light through a grating that is, say, white light, then it will be, as it were, diffracted according to its wavelength, because we've already shown that n lambda over d equals sine theta. So if lambda changes, then theta is going to change. And since red light has a different wavelength to, say, purple light, then what you will find is that the degree of diffraction will vary according to whether or not it's red light or violet light. And so a diffraction grating, if you put white light through it, will actually give you all the colours of the rainbow separated out very sharply. And in fact, a diffraction grating is better than using a prism. You may recall that you can use a prism to send white light through, and that will split the white light into its constituent colours and give you a rainbow effect. But a better way of doing that, better way of looking at the spectrum, is to put it through a diffraction grating, because you get a much sharper image that way. Finally, I want to look at what's called the refractive index. Light will refract when it passes through another medium, such as glass or water. And the reason is that the light slows down. C is the speed of light in vacuum, and it's pretty much the same in air. But when it passes through glass or water, then it will slow down. The frequency does not change. But since the speed is equal to the frequency times the wavelength, if the speed goes down and the frequency stays the same, then it must follow that the wavelength must go down as the light passes through glass or water. And we define the refractive index for a particular medium, let's call it glass, is equal to the speed of light in a vacuum, which is pretty much the same as the speed of light in air, divided by the speed of light in glass. That is the definition of the refractive index. And the refractive index for a vacuum or air is 1. If you have two media, air and let's say water, and you shine a light from air into water, it will bend. We call it refract. That will be called the angle of incidence, and that will be called the angle of refraction. And Snell's law says that the refractive index for air, which of course is 1, times sine of the angle of incidence equals the refractive index of water times the sine of the angle of refraction. That is Snell's law. Now you can, of course, transmit the light the other way. Let's again say that that's air and that's water, and we have a torch underwater and we shine it in this direction, and it will hit at an angle of incidence, like that. Now what happens? Well, some of that light will be reflected back off of this surface, and some of it will be refracted at an angle of refraction r. Now I think you can see that if you move this light round so that it's coming in like that, again, some of it will be reflected, but the refracted light will just travel along the surface of the water. And at that point, the angle of refraction is 90 degrees. And if you move this up any further, then all the light will be reflected, and that's called total internal refraction. And what we can do is to use this formula here to work out what's called the critical angle, the angle at which the light will only refract along the surface, and beyond that angle all the light will be refracted. And how do we work that out? Well, we have that the refractive index in water times the sine of the incidence angle equals the refractive index in air times the sine of the refracted angle. Well, we know that n air is 1, and we know that the sine of 90 degrees is 1, and that means that the sine of the angle of incidence, which is the critical angle, the angle at which all the light will be internally reflected, is 1 over the refractive index of water. And the point is that if you exceed that angle, then all the light will be totally internally reflected. Nothing will be refracted out of the water. And this is the principle of optical fibres. Optical fibres, which of course are made of glass, are designed such that all the light is always totally internally reflected. None of it is ever refracted out of the cable or the optic fibre. And that's why you can send signals down the optical fibre, because you don't lose any of the information, because none of it ever escapes from the glass. It's always totally internally reflected, however you may move this around. So you can use it, for example, to connect to a camera to take pictures in awkward places, including inside you. When people need to examine your insides, they can put an optic fibre with a camera on the end, very small camera of course, and they can put it down your throat to see what's going on in your stomach. All the light is totally internally reflected, so you don't lose any information. Columns like this, then a longitudinal wave will bunch some of these up and stretch some out. So at one moment you might have that kind of arrangement, and then the next moment you might have that kind of arrangement. There's, instead of it being transverse, going up and down, it actually goes in and out, rather like a concertina. Transverse waves can be polarised, because although I have depicted a transverse wave like this, in truth it can of course oscillate in any direction. If you were to look at that wave as it were head on, then you would see it oscillating up and down. But there's no reason why it shouldn't oscillate that way, or that way, or that way, or indeed in any way. And that's an unpolarised wave. Hello, today we continue in our A-level physics revision series looking at waves. Waves carry energy. X-rays penetrate your body. Sound waves can make things vibrate. Water waves can knock you over in the sea, and infrared waves can warm you up. A wave looks like this. And we say that the distance between two crests is the wavelength, lambda. And the maximum displacement is called the amplitude, A. We say that the number of waves, or the number of peak, the crest of the wave, the number of crests that pass a point in 1 second, is called the frequency. And we say that the time it takes for one wave to travel, for one crest to travel to the point of the next crest, is called the period of the wave, which is t. And t is 1 over f. Because if f is the number of waves which pass a fixed point per second, then the time it takes for each succeeding crest to reach this point is 1 over f. This axis here, of course, is simply the distance travelled by the wave. And waves have particular characteristics. They can be reflected, they can be refracted, they can be diffracted, and they can show interference patterns. The speed of a wave is the speed, like the speed of anything else. It's the distance divided by the time taken to travel that distance. And if we think that the distance is the wavelength, what is the time taken to travel that wavelength? Well, the answer is, of course, t. So the speed of a wave is lambda divided by t, but t is 1 over f, and so that is one and the same thing as lambda f. So the speed of a wave is its wavelength times its frequency, and that's its speed. These waves are called transverse waves, but you can also have what are called longitudinal waves, and sound waves are longitudinal waves. Basically, but you can force it to travel only in the up and down direction, and that would then become a polarized wave. And waves can be polarized by passing them through a polarizer, and the polarizer will take unpolarized light and polarize it in its direction, so it will go up and down. But of course you could twist this polarizer round so that it would only polarize light in that direction. You just have to twist it through 90 degrees and then the light will be polarized in this direction. What that means is that if we take a polarizer which will polarize light in that direction, then unpolarized light going through it will come out polarized. So here it's unpolarized, here it's polarized. If we then